How about I just give the outline?
Let me check if the stream is running.
Okay.
And then you have
Thank you for streaming.
When did we start streaming?
We have not yet successfully streamed one.
Yes, we have.
Oh, okay.
I successfully.
It's just we lost two. All right, it's running.
Okay. Okay. This talk is about how to rigorously. What did I say? Like this is like rigorously benchmark in reasonable time. So it has 4 parts. Which actually I'll write closer to. The first thing is like how to select. Well, it's why this paper is. I'm selecting a subset, a benchmark set.
What is benchmarking? Can you explain?
Yeah, I will get to that. Okay. The second part is like what kind of things do we have to do, like how to actually do the measurements. The third part is how to aggregate the statistics. And the fourth part is how to estimate error. Estimate uncertainty. So hopefully we'll get to all 4 of those things. Okay, so I was backing up. So benchmarking, that's like you've got a bunch of programs and and this is software benchmarking. So it's not like we're not gonna, so we're running them on a computer and that has like specific kind of like things you have to pay attention to and things you should be aware of compared to other kinds of just general metrology, which is the study of measuring things. So, okay, so programs, we're benchmarking them. Mostly we're looking at performance. Most of the times when you're benchmarking, you're looking at performance. And most of the time you're looking at wall clock time, but you could also look at other things. You can look at memory utilization, you got CPU utilization, other things like that. But generally, like you have some programs and you have some experimental conditions. I should go to the first thing we'll put up. Experimental condition, you run all like changes the execution of your program somehow. Don't know how, but different experimental conditions will change it in different ways, and we want to compare the experimental conditions. That's what an experiment is. Okay. So the first thing to like realize is that we can't actually test. We might not know the actual inputs that of interest. So we have to test kind of using like think of what would be like a representative benchmark set of programs that's representative of the infinite space of possible programs or possible inputs. So that's what kind of like a benchmark suite is. It's like a couple of programs that we think are going to be representative of all possible programs you can put in. How to get a benchmark suite and how to argue that it's representative is very difficult. So because the set of like for a C compiler, the set of possible programs is kind of like it's infinite in like, and it's very difficult to say like what a typical program that a C compiler would see is. Like I don't know. So one thing you can do is take a bunch of programs and look at certain features of the programs, like how many of this kind of instruction, how many of that kind of statement they have. And this gives you like a matrix where we put like program 1, program 2, and we have like feature 1, feature 2. So this is like programs and features, and each feature is like some real number, and this creates like a big matrix. And one way to argue that your benchmark set is complete and representative is if you span the feature space completely. Because then there's no way, even in theory, that there could be like a missing program because you spanned that space of all the features that you think are relevant. So that's like why you would think about it this way, is because you're trying to like sample an infinite space. So you like pick certain features and you make like points and you sample in that space instead. So yeah, but then this gives you like too many programs. So like you start with like as many programs you can find, and you want to limit this down to some point. Select certain programs that are representative, and then you only have to run those under all of your experimental conditions. You have like k experimental conditions and m programs. You have k times m different things to run. So we try to limit that as much So the way that you can do that is by taking this matrix and saying like, well, the simplest way is clustering. So clustering is like, if we pretend that this is 3 dimensions, and we'll see why in a second, and then these are like all points in space. So clustering is like these points are near each other somehow. So we only need to do one program from each cluster. But clustering is kind of like, it kind of assumes that you're, we'll see another thing we could do is dimensionality reduction. We'll compare it to clustering. Dimensionality reduction is like, if you imagine these as points in 3D space, but it could really be arbitrary dimension. It works. The intuition will work the same way for arbitrary dimensions, but you can't visualize arbitrary dimensions last time I checked. So,
Skill issue.
so if you imagine we're trying to go from 3 dimensions to 2 dimensions, we would find like the one way to do that while preserving as much, we have to throw away information to do that. That's projection. So we're throwing away like depth when we look at just the XY plane and like ignore the Z axis. So the kind of object is to like find a rotation of that 3D space that throws away as little information as possible. And kind of the way that you could think about doing that geometrically is to find the direction in which the programs vary the least and get rid of that dimension and like put that pointing right at you and get rid of that dimension. And now it's a 2D and you've thrown away the axis in which the programs vary the least. Does that make sense? What's up?
Is rotation the literal matrix operation you do to go from 3D to 2D?
Okay, so rotation you should think of it on the like a cloud of points. There is a way of writing a rotation in a matrix where you multiply by a matrix. And okay, so yeah, you multiply by some matrix to actually do the rotation. But when I say I want you to think about a point cloud, kind of like a bunch of points in space, and you're like,
Okay, yeah. And
Yeah.
then multiple programs on the y-axis. What are these?
These are
representing?
programs.
Programs in a software suite?
Yeah, programs that you're interested in, and that you think will be like, you should really use the programs that you think are going to show up in the real world somehow.
Okay.
So for a C program, we might take like the most popular things on GitHub that are written in C and put each of those as rows here. I should also distinguish between macro benchmarks and micro benchmarks. Macro benchmark is like a real big application and it's like really realistic, but it's really hard to understand. Micro benchmark is like, we're going to open a file 1,000,000 times in a row. It's very easy to understand, but very unrealistic. Does that answer your question?
Yes, so it's assuming that multiple programs have shared features.
Yeah.
Okay.
So it sounds like you're analogizing each feature to a spatial dimension.
Yeah, I missed that part, yeah.
And so each program has a different value for each feature.
Yeah.
When I hear feature, I assume it's either on or off. Can you explain what the values mean?
Okay. So this is like more like a machine learning feature, which is it could be on or off, but it's usually real value. An example would be like, so if we're testing a C compiler, it would be like, how many function calls do you make? Because we think that some compilers, the way they compile it, are going to slow these down or speed these up.
Okay, makes sense.
Yeah, and then so there's a real number in each of these spots, and I'm saying like that corresponds to a spatial location, so each program is a point space. So yeah, what's up?
Are these features ever actually materialized, or is it mostly as like the way of thinking about things?
Yeah.
It seems very difficult. to
Sure.
select.
Let's well, kind of. It's difficult but not impossible. And actually, we can just scroll down and then we'll find some.
Can we do more whiteboard stuff?
Oh, I have a webcam on here. I don't know if it's helpful.
I guess the question is, what features does this?
Yeah. So they use like different kinds of like low level architectural, like how many Dcache misses do you get when you run this thing as a feature? That's kind of an a posteriori, like you have to run it to know the
Yeah, I
feature.
have to say that that's not a feature you can know before you.
Right, but that doesn't mean it's not a feature. And it's actually one of the more useful ones. That's like all the a posteriori features are actually more useful in some ways.
Yeah, I think I agree. It just seems tricky.
Yeah. Well, you run in a simulator once and then you have all these features and then you reduce it.
But aren't these features also dependent on what architecture is being
Yeah. So this should be like interpreted as like on a specific configuration and machine and everything is specific. the number of L2 cache misses.
But if you have to run all of the things to get the data to know how to subset the things,
Well,
why bother?
you don't have to run them in all experimental conditions. You can pick one experimental condition, yeah.
So is the idea, as long as let's say you're developing a new architecture and you're developing it from some already existing base architecture, the idea is that you get these on the base architecture, make small modifications to make your new architecture, and then you can compare, and then use the data you already subset from the old architecture to
Yeah,
subset
but like
the
even more general, like people have like for x86, they think these are like benchmark representatives. So it's not just like, it's like, you should think about the pool that we're sharing the same benchmark set as like pretty big. And that's why like there's like millions, if you think of like every researcher who's working on this, there are like hundreds of experimental conditions, even if each experiment only has like 5. So yeah, what's up?
I just wanted to, so if you're saying like we ran it on this one architecture and it has these, so we think it's got this feature, aren't you like assuming that the architecture that was your initial trial run is a somewhat representative sample of architectures?
Yeah, yes, we're assuming that, and I think this is justified because the architectures are different, but they're not like so, because you're looking at the relative difference in D-cache misses. So it's really telling you, is this an IO heavy or like a memory heavy like memory bound versus compute bound? Even on, okay, so when memory bound means that like the program's performance is like mostly determined by how quickly you do memory accesses.
Yes.
And compute bound is like the program's performance is mostly determined by how quickly you can add numbers.
Fair. Well, I guess I interact with like user interaction things as opposed to like a lot of like, please crunch these numbers for me. So I'm used to like all programs are memory bound always.
I guess it makes sense that if the feature is the benchmarks in relation to themselves, which would have more D-cache misses or all, that would be more resilient.
Right, they're relative.
Yeah,
to each
that
other.
would be more resilient to kind of architecture specificities
Yeah.
than absolute numbers.
Yeah, that's a good point. So yeah, so now we have these points. So point cloud, we've rotated such that we have like the dimension in which they vary the least, which is not like X, Y, or Z, it's like a combination of them. It's like some vector where they vary the least in that dimension. You like switched it, projected it on that dimension. That's called PCA, right? I mean, that's what it's called when you do that. It stands for principal component analysis because the principal components are the ones you didn't squish, or principal component. Actually, they're all principal components but it orders them from like most principal to like least principal. Yeah, just to elaborate on the math a little bit more, if you started with a matrix that was like 100 programs by 5 features, so I'll write that bigger. This will like decompose it into a program that's like 100. So these are like 5 real features, but we're gonna like take the 2 most principal components, and those are like a linear combination of the features. So it's like mixing together some of the features with weights times a matrix that is 2 by 5. And so this is interpreted as for every program, tell me what are the values for the 2 hidden features that are the principal components. And this matrix is for every real feature, tell me how to get that feature given the 2 principal components. And you can, and then when you actually do this, then you can, you can do, yep. Don't need to discuss more. So people, it's not my idea. People have been doing that. So they did that. That's what they did here. So they took like 1 million features, or not 1 million. They took like a little more than 12 features, and they have the first principal component and the second principal component, all these programs, and they're kind of spread out pretty nicely. Maybe, I think they're saying you can ignore all the boxes because we already got circles that are nearby. Or no, actually, sorry, that's not what they're saying. They're saying the boxes and the circles are from different benchmark sets. So, but yeah, so you could say like, oh, maybe we don't need to test all of these because there's like a huge cluster right there. So this is actually, so we said we compare it to clustering. It's kind of way better. So in clustering, it's kind of like this, except each of the values can only be 1 or 0. Because you think of the coefficients in PCA, if you construct them to be 1 or 0, kind of like cluster labels. Like it's a 1 if it's in the first thing, if it's in the first cluster, and it's a 1 in the second thing if it's in the second cluster. So it's like a very restricted form. So clustering is like a very restricted form of PCA. So PCA is like more general, if that makes sense. And clustering, well, you get 1 from every cluster. That tells you that like you've represented the benchmark set that you originally had. But doing PCA tells you represented the space of possible programs, which is like what we actually care about. Does that make sense? If you say clustering and you just take 1 from every cluster, if your initial cluster, if you initially didn't have any programs over here, then your result won't have any programs over there. But if you do PCA, you'll notice where the holes are. So if we look here, we notice that there's some holes over here. So like they should like arguably hunt for programs that are at this like -4, 2 point, because in PCA we see the space of all possible programs, and we find that there's like some gaps in there that in the clustering they would just not know that they're missing kind of stuff in that way. So that's why PCA is kind of better than clustering in my opinion. And also, but yeah, you can combine them, so you can do PCA and then clustering. And if you do, instead of trying to figure out the number of clusters off the bat, you should do agglomerative clustering. This is a dendrogram, but what it represents is like agglomerative clustering. So you can imagine like starting with like everybody in one giant cluster that's like in the middle, and then you split into 2 clusters, maybe like 1 over here. They do mitosis basically, and then 1 over here. And then 3 clusters would probably be 1 over here, 1 over here, and 1 over here. And the radius of each cluster is kind of where the breaking point split is on this graph. So these 2 graphs show the same data, that's 6 and 8. But 6 shows you like at what the y-axis tells you like, or sorry, the x-axis tells you like where they split. So it tells you at a radius of 3.5, we have the first major split, like the first cluster breaks in half into 2 clusters that have smaller radii than 3.5. And then the right cluster breaks apart first, and then this cluster breaks apart next. Does this graph make sense? It's a dendrogram. It's like a tree graph. So it's like clusters, and then the clusters are clustered. You can think of it bottom up or top down. So bottom up is like you first clustered like really small clusters, and then you clustered the clusters, and then you clustered the clusters of clusters, right? So
How do they determine at what linkage distance to create clusters?
so this graph connects, if you give it an X, it'll make all of the clusters that can be connected with a radius of less than that X.
Then how do they determine that bound?
So you don't have to pick, this graph doesn't assume any particular bound. It sweeps through all possible bounds from 0 to 4. When we go test it, we're gonna have to pick a bound, because we can only test like we can't test all of the programs. So we cannot have a bound of 0. And when we test it, we kind of like see how much time we have, and then we split it based on that, is what I argue you should do. So if you have a lot of time, you should split it at 1.0. If you're like short on time, you should split it on 3.0, because then you have like fewer clusters.
It's like a timeline, it starts at 0 and then it increases linkage distance over time. It keeps track of which clusters have formed, and then iteratively clusters them until it gets up to 4. And you can see the timeline along the graph from left to right.
Indeed, you can interpret this at time, and people have done this for like human languages, like Proto-Indo-European, like human. It's like a general, and it's super interesting.
The opposite of that, because over time you're moving from less clusters to more clusters.
Right,
Because
yeah.
the process is artificial, so it's not the same.
Yeah,
as
language went
biology
backwards,
Where it goes down.
Yeah. So you play it backwards. That could be like languages or like, and people, phylogeny is a really interesting algorithm.
So you mentioned for PCA that there were holes
Yeah.
visible, but couldn't that just be an artifact of like the the amount of principal components we have and like the choice of like which principal components to display? Like if we have holes, those might be visible in 2 dimensions, but not in one principal component, right? I remember this.
It seems like when you go to higher number of components, you have a better visibility for holes.
Okay, so that's the situation.
Yeah.
These holes are present, and what we want to do is identify the lowest dimensionality visualization of like where these occur, like these blind spots in benchmarking occur?
I think the goal, is to say like for the biggest principal components should be well sampled.
Okay.
I think it's kind of like that's how I would say.
It seems like the edges of the ranges of these different components, like PC3 as an example, like there's just this one outlier or two outliers which are really far in that direction. Do we meaningfully say that there are holes because the right-hand side is pretty empty? Or is it just like, wow, those are wacky outliers, we don't care? Like, it's strange to call it a hole just because there's one thing that's making the corner mediocre there.
So I think that depends on if these principal components you think are like linearly related to your performance, in which case it doesn't matter how far you're away from zero, as long as you've got every direction, you've got a point. Or if they're not linear related, in which case you would care more about that. But also the outlier will break. It'll like make PCI prefer to pick that as a component, even though that might not be a good component. So this is difficulties.
Absolutely.
If we're trying to like look for areas that we think are like underrepresented by our benchmark suite when we do this, when we're losing information, is there a risk that we are like, we'll say like, oh, there's a hole here, when in fact it's like, well, the reason there's a hole there is because you can't, or at least it would require you to go out of your way to intentionally construct like a synthetic benchmark or a synthetic test program that produces that characteristics. So is there a time when it's like, we're not testing from that because like, that's just not how actual programs work in the real world?
Yeah, I think that's a good argument. I didn't think about that, but I think it's possible. And I think
Like something that does a lot of I/O but is also CPU bound, like those
That's
kinds of
impossible
programs
for
don't typically actually exist.
Yeah.
Because if you do a lot of I/O, you're probably I/O bound.
yeah, there are possibilities like that where I think this is where I think this kind of stuff is like, should be encouraged to think about it not as in like the rest of computer science people think of it as black and white. This is more of like, or art. Yeah, you argue about, I think you could make the argument, yeah.
But couldn't you also say that like with PCA, like those two features would be on like opposite sides of the same axis, so to speak?
Like the positive and negative.
Yeah, like,
What about the two features?
I mean, like if you're performing PCA already, you, like the reasoning of PCA means that you can maybe flatten some of that dimensionality into something lower level. So instead of considering like CPU boundedness and I/O, if you're performing PCA, couldn't you just reduce it to be like CPA boundedness on one axis, on one side?
Like the ratio between the two or the difference between the two.
Yeah, like I think if they're not orthogonal, right? So they're highly correlated. So I think PCA would already take care of that.
Yeah, PCA should take care of, we observe correlation, linear correlations, like more of this means less of that.
So I guess that's, like, wouldn't that kind of already be?
There could still be impossible points. Like it could still be impossible that there's no possible program because of like, there are limitations. Like it's not a purely linear space, and there are limitations on what programs like we can construct and programs would make sense. It's still possible that there's some coordinates.
You could have a program that is both like, I mean, it's a bad example for an impossible point that I came up with all the time. I guess, I don't know if we're considering like the ability to multi-thread, but you can absolutely be I/O intensive and CPU bound if you're doing like very exotic things and you have like asynchronous I/O, or your computer architecture allows you to do like hardware level like interrupt callback type behavior on like, oh yeah, your I/O is done now that you started like 200 clock cycles ago.
Yeah, I want to move on if we're okay with this. What paper was this? Okay. So this is the general Oh yeah, so this is somebody like, so that work, this work is super old. It's like 1990, oh no, 2007, sorry. 2007. This work is newer and they like summarized all of prior work and gave you like a really good like flow chart. So if you're actually interested in doing this, here's a flow chart that, and look, PCA is part of it. They use a modification and then they do clustering with elbows and then they choose a subset. So that's kind of cool. And I think
What's the title?
I'll put it. No, the title of this one is bench subset. The next title is producing wrong data without doing anything obviously wrong. But first, I just wanted to, I guess I do have, I forgot about this, but yeah, what am I saying? I have okay, I'm just gonna skip to this for now. So okay, so this I think is done. The second part, how to actually measure. So this paper is going to be kind of about that. So they did some programs, and they did this program. So figure A. Yeah, I guess it like add some numbers to themselves. And figure B, they added a certain amount of like environment variable before running the program. Like they added like A equals something as an environment variable and then ran the program. And this is the length of the environment variable that they add. And so this is bad because it tells you that based on what your environment is, it like speeds up or slows down the program, which is like, that's crazy. So the reason that this happens.
How does it say that? I mean, how do you know that's not just like noise? I don't see any trend there. Let's fly to this flash.
So because sometimes it's 6,000, but sometimes it's 8,000.
How is that? But how can you say that's not just noise from? If you had no environment variable and then you just ran it, however many dots that is.
Oh, okay. So each dot tells you, each dot is actually a distribution. It's harder to see, but this little I-beam looking thing is actually a distribution.
So it looks like for all the even numbers.
There's some periodicity.
Yeah, there's some periodicity.
Oh, this is some 70 bullshit, isn't it?
I think it's some buffer length bullshit. So
Well, that's basically the same thing.
this is not fitting on the screen. But basically
I
like,
think you're very zoomed.
yeah, it's some Wayland problem, I think. So if this is your environment and you've got the A and B, and this is one cache block, then by changing the length of your environment, now A is in the same cache block, but B is in a different cache block. And I'll say that the environment always gets loaded when in every main method, the first thing on the stack is the environment. And then there's all your variables. So it can push the alignment.
That probably explains the big single jump in the graph, right? There's like the periodicity, but then there's a dot that's like super high up. That's the only one. That's probably what's happening.
That could be, yeah. It also just changes like the relative offset between things, or if they're aligned. So A and B are like no longer, even if they're on the same block, they're no longer block aligned.
How big is the cache block, and does that also explain the small periodic
I think,
changes?
yeah. So there were like a bunch of caches. The smallest one I think is 64 bytes or 64 words. It's a cache line.
It's depending on your machine. It's either 64 or 128. On Intel, it's usually 64. On Mac, it's usually 128.
So you could definitely be like pushing you over that, pushing two variables that are on the same cache line into different cache lines, and then into the same one again. So yeah, so definitely like that's super sus. We don't like it. That just tells you. Some people say because of this, you should use it. Turn this off. Like turn off address space layer randomization and use a fixed environment. I think the other way, you should actually sample across this variable, because this variable can speed up some programs and slow down other programs. It has like it's not always going to slow everybody down uniformly. So instead of like picking one and always using that would be more reproducible but less representative of real world performance. To be more representative, even though it's more noisy and less reproducible, you should actually vary. You should actually look at all of these points. Like if you just looked at one, it wouldn't be telling you the whole story. You have to look at all of them basically. So you actually should randomize this variable, in my opinion. But there are a lot of guides online that say like, oh yeah, the first thing we did is, and a lot of papers, okay, the first thing we did is turn address-based layout off, randomization off. So, yeah.
Is this such a problem that you can't just ignore it? I mean, 5%.
Well, so let's see. So it's going from 60 to 80. That's more than 5. It's like 20. That's like 30%, right?
What is the one modifier?
No idea. They don't say. I read the text like 3 times. They don't say. I should. They're from 2016 though.
They were
So
playing a game of Counter-Strike.
yeah, I don't know. Actually, are they 2016?
Well, thanks very much, Ronnie.
Oh, they're from 2009. So definitely not. What was in this? Oh yeah. Wait, was I here already? Oh yeah. Okay. So this is Julia. Oh yeah. I think they're gonna say. Okay. So here's their benchmarking Linux tips.md. So I was looking at these. So one thing that they do is they say to use CPU set, but nowadays you're supposed to use you're supposed to use C groups. So C groups like they take your system resources and they guarantee a certain allocation. You can control how your system resources get cut up. So you can tell C groups to give this process 2 CPUs and a certain amount of memory. And then you can tell actually every other process not use that using systemd. That's what a slice is in systemd. So if I go, you know, like a systemd slice, like if you ever done, okay, where'd that go? System till units type slice. So here are the slices. They're hierarchical. The root slice for some reason is called dash. I don't know why they did that, but dash.slice is the root. And then everything inherits from that. And then it's like all hierarchical. So if your parent doesn't have something, that means you don't have it either. And you can change this, change all of the. So then if you look at the info, I think it's this. Show, oh no, system show.
No, it's yelling at you because it thinks the dash is.
Oh.
Like a.
Yeah. Okay, so these are the resource limits that are configured on the root, which is usually nothing. But it also doesn't not just tells you limits, it tells you the kind of current utilization. So what I do is I turn effective CPUs, I like omit, I say it's like, no, not 0 through 7, like don't use CPU number 2, and then I'll tell somebody else you can only use CPU number 2 in my benchmarking. So that way it's got a CPU. There's something called a SMT sibling, which means that an SMT sibling is like they share, these 2 CPUs like share a bunch of like functionally like, you know, like microarchitectural functional unit resources. So you also turn off the SMT pair, which is a fun kind of, it's in the procfs. Actually, I don't know where it is exactly, but it's in the procfs somewhere. SMP is simultaneous multiprocessing. That's like you've got one Linux and it's got like 5 cores. SMT is simultaneous multi-threading.
I think SMT is symmetric.
You're right, symmetric multiprocessing. SMT is symmetric simultaneous multi-threading.
They have different S's, which is
Yeah. You can read more about it here. Oh yeah, they tell you how to do it. So they go here. Yeah, here are your siblings. So cores 0 and 4 are like sharing a bunch of stuff. So if you want to test on core 0, you should turn off core 4 so it doesn't get interference. And I think I just saw it a minute ago. They say disable this. So in my opinion, this is not actually good. You shouldn't actually disable this because then you're only getting one of those points in that figure we saw earlier. So I kind of disagree with them here. Yeah, and then they turn off, you can like, this is kind of cool. I didn't realize all this stuff was like through the file system. Like, yeah, you can just like turn off processor frequency scaling by just echoing something to a file, and now your processor.
Technically doesn't turn it off, it just makes it more aggressively run CPU. There is other ways.
Yeah, there are other ways to turn it off.
Fixed frequency, but they're often very slightly between what built-in hardware there is for automatic frequency scaling and what company made your CPU. So it quickly devolves into a nice messy compatibility matrix.
Yeah. So anyway, so you can like set all these stuff and it'll like turn off frequency scaling, it'll turn off hyperthreading, but don't turn off address space layout randomization because that's actually good. And then, yeah, you can learn more about C groups. That's how Docker works. Docker is just a wrapper around C groups and namespaces. Oh yeah, and so I made all this into a set UID binary. That means that you don't have to be root to run it, but it runs as root. So I can like ask you how to do that. And I actually didn't know about I didn't know the details of set UID. This paper is really good. It's like demystified. That's actually an honest title. Like it does it's like this mysterious thing, and then they just give you it's like
Wait, what was that?
this is if you like don't use a simpler. This is at the low level. If you don't use like a simple high level construct, that's what it is. But they give you a high level. They give you, is it figure 8? They give you one of these things that's just like a way of simplifying. Oh no, it's figure 13. This is the simplified state machine that you should actually use. So like if you're not using this, then you're subject to that other state machine. So this is cool. Yeah. Okay. So I say we learned how to measure. We just turn off a bunch of stuff. There's address space that we actually keep on, and that's big asterisk because I think everybody else is wrong about that.
Everyone everywhere should agree to turn off SLR because it doesn't actually make you that much more secure.
Yeah, it does make you more secure, and it makes your sets be in a different order. It makes your hash sets be in a different order every time you run your program. So, next one is how to aggregate this stuff. So this is a table. This is a fun title: How to Not Lie with Statistics. So let's reproduce table 3, the calculation in table 3. Yeah. So let's say we have benchmark program. I'm using my annotation. Program 1 and program 2. Let's say like program. And there are 3 experimental conditions: X, Y, and Z. X, Y, and Z. This is like math magic, so you better watch my slide at the end here. So these are the performance, the raw kind of numbers: 20, 40, 10, 80, 40, and 20. So what we're going to do, I'm going to leave some room to work, is, okay, so now I'm going to hide this, and we are going to say these numbers are like absolute seconds. They don't actually mean anything. Like we want to normalize them all because we're going to say which machine is faster. So we're going to normalize them all to machine X. So Y would be like 0.5. Z would be 2. So it's like twice of X and half of X, right? This would be 2, and this would be 0.5. So the average, and these are all 1 implicitly because we're normalizing to X. So the average of this is 1.25. The average of this is 1.25. And the average of this is 1. So we say on average, Y and Z are equal when you normalize to X. Okay? Now I'm going to do the same thing, but I'm going to normalize. I need to check what they normalize to next. They normalize to Y next. So remember, if we normalize to X, this is like, and we average, we get these numbers. If we normalize to Y instead, we'll get 1s here. We'll get a 2 here, a 4 here, a 4 here, and a 2 there, right? Oh, I messed this up. So this should be 0.5 and this should be 0.25. Is that right? Okay, you gotta be watching me because this is crazy. Because we do 4.25 and we average these, 4 and 0.25, we average these and we get 2.125. This is 1, and we average these and we get 1.25. So without changing the data, we normalized to Y instead, and now we get that Z is much slower than Y. Did I make a mistake? If we normalize to X, Y and Z are the same. If we normalize to Y, Z is much slower than Y.
Assuming these different machines are better at different kinds of tasks, based on which one we normalize against, we're implicitly prioritizing different internal performance abilities as more heavily weighted, right?
That doesn't make sense to me, but like I think we can agree that this is confusing. That doesn't make sense to me because you're normalizing to it. So you're saying like, even if y is faster at this certain thing, we're doing like, how much slower is z than y? I don't know.
Fair enough.
Just to put that up, let's say you're also normalizing both categories, which.
I'm normalizing both categories?
Well, yeah, across both 1 and 2, the properties 1 and 2, you know,
Yeah.
equally different information.
Yeah, they could. Let's say like I change all the benchmarks so they all take a second. And that's instead of normalizing by dividing, I'm just changing the benchmark run length. Now they're all 1 second and now they're all kind of the same and they're all the same units.
Oh, I mean, I guess I was going to try and clarify Jen's point because I think it's correct. But like, since, yeah, I guess when the normalized, I don't know how to put this in words yet, sorry.
Well, let me ask you this. If we normalize to y, should the things that y are good at get faster or like, will it make the things that y is good at matter more or less?
It'll make the other things scores on them matter less.
I see. I mean,
The
okay.
score on 2 when normalizing y barely contributes to the arithmetic.
Yeah. Yeah.
Because it's so small compared to y.
So, but then, okay, so then this like kind of invites the question, who should we be normalizing to, x, y, or z in this graph, or in this table?
Doesn't the geometric means?
Yeah. The geometric mean fixes. That's what this paper is about. So you got it. Correct use of the geometric mean, and they say everybody would have one. So the geometric mean, okay, so the arithmetic mean is like normal, like you add them up and divide by 2. The geometric mean is like you multiply them up and you take the square root. And actually, it's like the same in log space. It's like you took the arithmetic mean in log space and then took the x. So if you do that, you say, it doesn't matter who you normalize to. If you, I would just erase the numbers. But if you just multiply them up and take the square root, it ends up being the same. You can show that because I think it's like if you do the square root of x1 and x2, but then you compare it to the square root of x1 scaled by y1. Oh yeah, so you're comparing this, right? y1, y2 compared to, this is like normalizing before taking the mean. And this is like taking the mean.
The trick is just that when you want to compare norms, you want to do multiplication and division.
Yeah.
And then when you multiply it in square root, you're basically, that lifts into addition and subtraction on the exponent, which is what you want.
Yeah.
Whereas if you do it arithmetically, then you're doing
addition and subtraction on
and then
the ratios.
parentheses, then you're doing subtraction or division on the ratios, and that doesn't lift.
Yeah, it does, and it doesn't make sense to add normalized ratios. It only makes sense to multiply them.
Yeah, that too.
Yeah, and like, if your metric is very small, then like differences between small values will matter artificially less.
Yeah.
And, you know, similarly, the differences between large values, I guess.
If you're, wait, say that again.
Differences between small values, if it's like an order of magnitude difference between something that's a tenth and 100 as fast or whatever, or slow, that matters artificially less in arithmetic than like a 10 to 100x increase.
Well, I think, yeah, we'll discuss more because somebody wrote this. Somebody else wrote why it was completely wrong, garbage, like 0 IQ. And then somebody else wrote, and this was 1986. This one was 1983, I think. I can't find it right now, but then this one is a response in 1986, and then this one's in the years. This is 1988 now, and then this is 2006, and people are still arguing about this, and like, Jesus Christ, like, so this is like timeline, what do they call it? The war of the means, and there's also harmonic mean in here, and nobody agrees, and they're like, they detract from the geometric mean and like all this stuff, and it's like this timeline of these battles that took place on a journal that nobody reads.
I hope geomean is correct. That's what I'm.
Well, okay, so I think it really depends. So here's another break teaser. So if you have 2 runners in a relay race, one of them runs 20 miles per hour. These are like cars or something, and the other one runs 30 miles per hour. What's the equivalent rate that one person would run that would equal the equivalent for the two. Like equivalent, like, so one person runs 20 miles an hour for a mile and gives it to somebody who runs 30 miles an hour. What would be the equivalent speed if one runner who did both segments by themselves? It would finish at the same time, maybe their equivalent speed.
Depends on your assumptions about humans.
What? No, like one runner goes 20 miles per hour and they do a relay. It's a relay race. And they hand off their baton to the second runner who goes 30 miles an hour the entire time. And then they finish the race.
You're saying like which one performed better?
No.
Say, what's the equivalent, like, constant speed?
Yeah.
Oh,
Depends on the system.
What's good?
Oh, I was gonna say, like, if we're doing the relay race thing, then it's like, you have to consider like the distance.
Yeah.
Traveled and
Yeah.
the amount of time, and then-
Assume they run the same distance. Okay, 25. Thank you for being bold, because this is a trick question, and I thought it was 25 like the first 7 times I did this.
Thank you for being willing
Oh, is this
to
the thing
say
where you
all
reciprocal add
right
and reciprocal
So
If you run, the first guy runs 20 miles in an hour, the second guy runs 20 miles an hour.
your camera.
So then you run 40 miles in total, an hour 40 minutes.
You're doing so much.
So okay, yeah. No, let's just go over this. So it is 25 miles an hour if they run for the same amount of time. So the slow guy runs an hour, the fast guy runs an hour. The equivalent would be 25. But if they run the same amount of distance, the slow person spends more time running because it's the same distance, and the slow person takes more time. So the slow distance, then it's 20 mph, 30 mph, and if it's a mile, for example, they run a mile in 3 minutes, right? So we say like, so miles per hour is the same as, so 20 miles per hour is the same as 3 miles per minute, or no, 3 minutes per mile, right? I just did 6, flipped it around here. This is 2 minutes per mile. So the total run would be 5 minutes if they both run 2 miles. And this person runs for, this is 20 times 3. Wait, what am I doing? And then 30 times 2 divided by 5, which should be 60, 120 divided by 5, which is 24 miles per hour, unless I made a mistake. And the reason it's relevant is you replace miles per hour with million floating point operations per second. And you see the analogy to computing now. So I think the reason why I think the way that they resolve this is kind of wrong, or kind of maybe it's actually not that one mean is better or worse. It's they depend on your generative model. So arithmetic mean kind of, do you have something?
But this is just another example of the arithmetic mean being bad. Because.
Yeah, and the geometric mean too.
Oh.
I mean, this is basically geomean versus harmonic mean.
Yeah, or all of the means versus each other. So yeah, I just did, yeah.
Which mean is 24?
This should be the harmonic mean, because when I flipped it around, I did the reciprocal, and then I did something, and then I did
It's 1 over.
Yeah. Or it should be 2 over, because we're doing 2 numbers. 2 over, 1 over, and plus 1 over n. And then, just checking the time. So arithmetic mean assumes that you don't know which program they're going to run, but they're going to run one of those programs. What's the expected value? Geometric mean assumes we don't know which overhead we're going to experience, but we're going to experience one of the overheads that they measured. What's the expected value? And harmonic mean tells you if that every second I'm going to flip a coin and I'm either going to be the slow relay guy or the fast relay, or not every operation is either going to be done by the slow person or the fast person. How long will it take to do 1 million operations? That's the harmonic mean. So it just depends on how your benchmarks relate to the actual input that you're going to see. So if your input is the composition of a large number of your benchmark dudes, then harmonic mean would be appropriate. If your input is literally one of your benchmark programs, then arithmetic mean would be most appropriate. If your input is something unrelated, but you think it has the same overhead as one of your things and you don't know which, then use the geomean. I think geomean is more often that you have that set up. But it really just depends on your relationship.
I use it in the context you're trying to measure the speed up on a fixed set of benchmarks. So you
Yeah.
have like different configurations.
Yeah.
So you don't, in some sense, you don't know which of the overheads.
Yeah, you know which of the hurdles you're going to see. But if I'm going to like flip like pick one of your benchmarks from a deck of cards and run it, the expected value would be the arithmetic mean.
Yeah.
So it just depends on how your actual input relates to your benchmark set and the generative model there. But yeah, I think geometry mean is often, and it's nice for like ratio for unitless ratios. Geometry is like good. Yeah, so I think that covers summarization, like aggregating. So use the geometry. It depends on your thing, how you aggregate. So okay, so then I looked at this benchmarking flaws paper. Like the number one flaw is not putting an error metric, like no uncertainty. Like the speed up is 12.52%. What's like I'm not telling you the uncertainty. Like so it's in, like is it exactly 12.25%? Is it like plus minus a little bit? I don't know. So that's a big problem. So and in this case, I promised a little bit of calculus. So some people do the min. They like, I don't care how long, like the min is like, there must be like some minimum code path through the architecture. And everything else is just a little bit like the min plus something. It's like you deviate from the best optimal case code path. So they'll just measure the min. They'll like do a million things and just look at one point, which is the fastest time it ever went. And that is actually how many of your users will experience the min. It's like exactly like very few, like very small chance of actually getting the min for your users.
If anything, if you were gonna do that, wouldn't you wanna take like your maximum and say, well, we
Yeah.
at least this or better?
People who do latency in servers do max for that reason, because even 99th percentile cuts off like the things that they care about the most, which is the max, which is the heavy tail on the positive side of the heavy tail is what you care about in a server. And the reason is because let's say you have like a 1% chance of getting the 99th percentile latency, right? But let's say your Google Drive shitty web app needs to talk to 10 microservices to actually load the first time into the user can type. It needs 10 microservices. So what's the probability that any one of those 10 experiences the 99th percentile latency?
It's going to be 0.99 in the code.
1 minus 1% to the power of 10. And how would we approximate this? Like, I don't have a calculator.
0.9.
How'd you get that?
Not a good way.
Okay, so this, we're going to use so we could use Taylor's theorem, but binomial theorem is a special case, which is like equivalent. So we use binomial theorem here, which the intuition, of course, is that if you actually had 10 copies, for a lot of people, they've seen this like a million times, but I have never seen it explain why we get a combinatorics in my algebra. So if you actually had 10 copies of this and you're doing FOIL on each pair and you do FOIL and you do FOIL, it's basically like taking one from each group, either 1 or negative 1% from each group. And then that's going to be a term in here. So I could have a term that's like 1 to the power 10, plus I could have a term that's 1 to the power 9 times 1% to the and then plus 1 to the power 8 plus 1% to the 2, which is if I pick 2 of these, I get the 1%, and everything else I get the 1.
I think you need to add some minus.
I need to add some minus signs, yeah. So it was negative 1% and negative 1% squared, which is just 1%. And then the other thing I need to add is the coefficients. There are actually 10 ways of picking this, which is to pick one of the 1% and the 9 of the 1s. You could do 1%, 1, 1, 1, 1. You could do 1%, 1, 1, 1. So actually 10 choose 1 way of doing this, 10 choose 2 ways of doing this, right? So, and this is the great thing about computer science. Okay, so we did minus 1%. That's what this is, right? I'm going to say everything else is big O of 1% squared. So in computer science, when X is big, you write down big O of the highest power and you ignore the lower ones when X is big. When it's small, you do the opposite. You write down the lowest powers and everything else is a percent of a percent or percent of a percent of a percent if you were to keep going. So everything else doesn't matter. So we write down the highest powers of X of 1%, and then we say big O of everything higher. It's completely opposite. But I think it's nice. Like, I think that's nice. So anyway, so we get to the overhead, and actually, and the reason we did this is so that we can put an N here. So the overhead, okay. So the overhead we would get would be N choose 1, which is just N times negative 1%, which is just 1 minus N%. So you were right when you said 90%. I don't know how you did that.
I think the way I actually did it is just like, you do it 10 times, roughly every time you're subtracting around 0.01. And so that gets you to 0.89. And it's like, well, not really. I mean, by the time you get to the end, it's like a little less than that. So 0.9.
Okay, well, that is so the more microservices you have, it's linear. To a first order, it's linear. So you start out, your probability of hitting a 99th percentile latency starts out at 99% if you've got only one microservice. And then it goes down linearly with every microservice you add. So basically where Discord is now, I mean, it doesn't hold as you get, you need to start considering the higher orders eventually.
Oh, linear is what I mean.
This is linear at first. The higher orders, the more you go out,
Yeah,
the
higher
less it
orders.
is.
So you mentioned like metrics of uncertainty, and there's a variety of ways people can present uncertainty. Like people can present standard deviation, and they can
Boo!
go back a step and be like, okay, well, here's the like intrinsic uncertainty in our sampling, like as
Yeah.
in terms of like our like confidence in it.
Yeah.
So
So which one?
yeah.
All right, let's go. I'm just going to continue. That's where I was headed. Okay, so I think that they should do, so this is showing you normal and log normal. And I think that they should think about what underlying distribution it would be, and then think about the MLE estimate for that distribution. I think that's the best way. So the reason I'm showing log normal and normal, because programs are not actually normally distributed, even though everybody assumes that they are. So we're getting to the blue sky, like, oh, hi, everybody. Hello, kids. What probability best models running time of programs? So I'm trying to make a community that people talk to each other about this kind of stuff. And I don't know if Blue Sky or Mastodon is the right place. So somebody said something useful, try Gamma or Weibull. Somebody else said, did you know that software development is a random process? Okay, whatever. And somebody else kind of argued with me. They're like, oh, you can just assume it's Gaussian. I was like, okay, here's an example where it's like very not Gaussian. And they're like, I wouldn't trust that because you're using Python. It's like milliseconds. And I was like, okay, look, here's the actual accuracy of my timer. This is an undeniable right skew. Like there's almost nothing less than the mode, which is this spike. There's a lot more than, and it looks like a comb because it's a granularity of 1 millisecond. And this person's like, yeah, see, it looks normal. That's what I tell you. More like a Gaussian. Yeah. I'm like, bro, what? It has an undeniable right skew. But
Okay, I might have to install just for this.
you don't have to install it. It's all public. So I realized that even though this person, I looked them up, they're like a scholar of this stuff in computer science, and even though they're a scholar, it's still fighting with someone on the internet is still fighting with someone on the internet. So what I'm gonna do is I want to have more data right now, but I want to get more data and actually figure out what distribution. So I've been using log normal, which if you think about, we said logarithm is the same as geomean. If you just log everything and then pretend it's normal, that's the same as doing the geo, or the expected value would be the maximum likelihood estimate would be the geomean. So it is kind of look log normal, and log normal has this property of infinite divisibility where if x is log normal, then for any n you can cut x up into the sum of n IID distributions. So it's like if you think your program is log normal, it's composed of instructions that are operations that are log normal, which are composed of instructions that are log normal, which are composed of assembly and then microcode all the way. And if all of those infinite divisibility says that you can use the same distribution and it aggregates to itself, the sum of log normal should be log normal.
So it's kind of like when you can sum normal distribution to get a normal.
Yeah. It's like that. So that's nice. I actually think it might be gamma distribution for some reasons, but I will get back to you when I have more data. And then we talked about uncertainty quantity. Where does the uncertainty come from? There's actually a couple of places. Part of it's you actually don't know your timer. It sucks. It's only good to a millisecond or whatever. That's epistemic uncertainty or measurement error. Actually, there's also aleatoric uncertainty, which is actually like, even if you had a like super precise timer, the actual underlying phenomenon takes different amounts of time. You're trying to estimate the hidden variable, which is how long, like how much time it should take, and you only get to observe how much time it actually takes. Or like you're trying to estimate these like these parameters on some like imaginary distribution, and you only get to view the draws of that distribution. There's uncertainty there. So you actually have this distinguish where it comes from, whether it's aleatoric or epistemic, and you actually add them both. You get both, and you get measurement error, and then you get. So I think what you should do actually in practice is time a no-op. A no-op should take almost the same amount of time, which is almost 0. And then that tells you the overhead of your timer. And then so another thing you should do is like, because of the address space layout issue, you don't just run it once. You have to run in different processes, not just in the same process, I think, because that's the only way to defeat the address space layout. So you have to average within, or not average. You have to summarize or aggregate within process and between processes, I think, in order to get a good, actually do this correctly, in my opinion. And then, oh yeah, and then like, can you imagine if that was supposed to be about p-values, I